Okay, this is the second part of the ocean circulation chapter. This lecture is going to be a little bit shorter than the last one, which is probably fine by you, because there are only three kind of mini topics that we need to cover with regard to ocean circulation that we didn't get to in the last lecture. So let me bring those slides up here and we'll just get started. Okay, so there we go. So we talked about atmospheric circulation in the last unit, so this slide should look really familiar. In fact, it's the same slide we used in Unit 2 when we talked about how the Hadley and the Ferrel and the polar cells circulate and how the Coriolis effect shows the movement of these air masses taking these curved paths across the surface of the Earth. But what we're seeing here, it's highlighted in the middle of your slide, is the intertropical convergence zone. This is the boundary near the equator between the two Hadley cells. It's where, if you want to, do the dance, it's where the warm, humid air forms and rises and expands and cools and precipitates. And it's that precipitation, which is why at the intertropical convergence zone, there's a lot of precipitation, rainfall in the tropical rainforests and jungles of Southeast Asia and the Amazon and sub-Saharan and Central Africa. But the intertropical convergence zone, as drawn on this diagram, isn't always at exactly the equator. These diagrams are like idealized scenarios, and there's actually more variability at play here. The true location of the ITCZ is on this next slide. In July, you'll see it's the red line there, north of the equator. And in the winter season, or our winter season, the month of January, it shifts southward. But you'll also notice that in the Pacific and, let's see if I can highlight here, in the Pacific and the Atlantic Oceans, it doesn't shift all that much. Water has a high heat capacity, so it's slow to warm up and it's slow to cool down. But over here in the Indian Ocean, you see that the ITCZ shifts wildly from summer to wintertime, really far north in the summer, all the way into Southern Asia, and really far south, well below the equator in what would be our wintertime. And that doesn't happen in the Atlantic or the Pacific Ocean. And the outcome of that, the result of that, is something very unique in the Indian Ocean that we didn't talk about in the last lecture. What we see here in the Indian Ocean, we see, I'll get my little laser pointer here. We see there is what's called the SE, the South Equatorial Current, and the North Equatorial Current. Those names match up with the names of the currents that we were seeing in the last lecture. We see that we have the trade winds here pushing on the South Equatorial Current at that 45-degree angle that we mentioned in the last lecture. And we also see what's called the monsoon winds up here in the Northern Hemisphere, also at that 45-degree angle, just like the trade winds in the Atlantic and the Pacific Ocean. So everything we're seeing here in the wintertime is pretty standard according to what we were already seeing in the other oceans from the earlier lecture. But when we move it to summer, we start to see something very unique happens here in the Northern Hemisphere with those monsoon winds, as they call them. They completely turn the opposite direction. The winds in the winter are blowing off the land out onto the water, and in the summertime, they're moving off the water onto the land. That creates monsoons in Southern and Southeastern Asia that don't exist anywhere else in the world, because this is the only place where that happens. This is the only place where that happens, if you go back a couple slides, because it's the only ocean that doesn't really have much of a Northern Hemisphere component to it. It only has the one gyre in the south. There is no northern gyre because India and Southern Asia basically gets completely in the way of it. So what's the result of that? The monsoons, when those winds reverse, it creates very different seasonal weather patterns, specifically heavy rains. And I don't mean heavy rains like we were seeing here over the last week or so. These are, as you can see from these images, just heavy heavy, almost like torrential rains, and they don't last for a few hours or a few days or a few weeks. These can go on for weeks and weeks and weeks, maybe even months. As you can see from these images, causing serious levels of flooding and flash floods and erosion and landslides and mudslides. This guy over here, I don't know if you can see him, if I can kind of highlight him. This kid right here is just loving it, but it can cause some serious damage. It can cause some serious economic disturbance. It disturbs the way of life. But if you're clever about it, if you're kind of savvy about it, you can put that excessive amount of rainfall to use. And that's what many folks in the agricultural regions of Southern and Southeastern Asia have done. And the staple crop that they grow there and they use to sustain very, very large populations is rice. Rice is a crop that you grow in shallow pools of water called rice paddies. So these excessive amounts of rain, they can collect it into reservoirs and then use it to flood and sustain the water levels in those rice paddies, allowing them to grow enough rice to feed literally billions of people. So this is what we see in the spring and summer months in those monsoon seasons in Southern Asia, is that we want to look at what is the air doing as it moves along the surface. So again, I'll try to highlight it here. As it moves off the water and onto the land, what's the air going to do? What happens to the air out there over the tropical regions of the Indian Ocean? Well, it's something we've already talked about numerous times before. The air over tropically warm water picks up a lot of the heat from the water. It picks up a lot of water vapor due to from the evaporation taking place in those waters. And so we can do the dance. We have warm, humid air. And as you see in the image, it gets pushed onto the landmass, Southern Asia, India, Southeast Asia. And because it's warm, because it's humid, it will rise and expand and adiabatically cool and condense and precipitate. But what they have specifically in Southern Asia is the air doesn't just rise on its own. The air gets forced upwards along the foothills and the southern range of the Himalayan mountains. So you have this rapid and vigorous thrusting upward of this warm, humid air mass. And so the amount of precipitation you're going to get out of it, kind of like at the cold fronts that we studied in the last unit, it's a heavier amount of precipitation. And because these winds aren't, your local weather pattern winds, these are essentially those trade winds, those, as we referred to them before, strong and consistent winds. This warm, humid air getting pushed onto the land, it's happening all day, every day, like I said earlier, for weeks, maybe even months at a time. And it's just rainy, 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 heavy rainy, nonstop. And then we get over here to the winter months and we start to see the entire thing flips around. This is what it looks like in the winter. So the air mass is blowing off the land onto the water. And we can see what happens there, this air blowing off the land onto the water. Okay, everything's fine. But then again, as it blows over the warm tropical water, the air will pick up the heat, it will pick up the humidity, and it will, do the dance. It will rise, expand, cool, condense, and precipitate. But that precipitation in the winter months happens way out here in the Indian Ocean. So there is a winter monsoon season for places like Madagascar and some smaller island countries in the southern Indian Ocean, while the mainland of Southern Asia and Southeast Asia, that kind of dries out. Wet during the spring and summer due to the monsoons pushing this air onto the land from the warm ocean, and it dries out in the winter from the monsoon winds, the trade winds blowing the air off the land out onto the central and southern Indian Ocean. Okay, so that's it. That was the monsoons. Again, a little mini topic that we didn't get to in the last lecture. Next mini topic is something very unique in the Pacific Ocean. What's unique about the Pacific Ocean is its size. It is massive. It is 2 or 3 times the width of the Atlantic Ocean. So these north and south equatorial currents seen here, they spend so much more time traveling across the Pacific Ocean, that they are given time, as you can imagine, like water heating up in a pot on your stove. The more time you get it, the more heat the water will accumulate and the higher the temperature will become. And so we mentioned this earlier when we're talking about hurricanes, how over in the western part of the Pacific Ocean, there is a huge pool of warm water over there. This is why there's such a huge pool of warm water, because the equatorial currents push it over there. And then the way that they behave is they are strong currents because they're being pushed by the trade winds. Push, 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 push. The winds are pushing that way. The currents are flowing that way. And so that all ends up kind of holding, if you look at my hands on the video, I don't know if you can see my hands, everything's pushing. The trade winds are going across the ocean. The equatorial currents are going across the ocean, and that has a way of kind of like push, 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 and it holds this pool of warm water on the western side of the Pacific Ocean. And we're back. Okay. There is an equatorial countercurrent here, but it's just a little bit of water that has to kind of get squeezed out of that western side of the ocean. Because something's got to give. You can't just pool all of this water over there without some sort of release of the water that was there earlier. So a little bit of water cruises between these equatorial currents for two reasons. It's kind of getting squeezed out of there. And the second reason is something we talked about before, the Coriolis effect near the equator, it's almost zero. And so without a Coriolis effect there, there's a little bit of water that can kind of go the other direction. It's slow to go the other direction. Kind of like, if you think of it like you were walking through a crowd of people and they were all, say, like leaving the movie theater or whatever it was, a big crowd of people, and you like forgot your wallet inside, so you're trying to get back in against the flow. It's going to slow you down. You can still get there, but the flow of everybody coming against you, like these north and south equatorial currents, it's going to slow you down. So what we have in the Pacific on a normal year is this thing called Walker circulation. Walker circulation says the trade winds are strong, the equatorial currents are strong, and there is this, as you can see on this temperature diagram, this Pacific warm pool, this huge amount of warm water. It just kind of sits and gets held over there on the western side of the Pacific Ocean. And because there's so much warm water on that side of the Pacific Ocean, the thermocline is deeper on the western side of the Pacific Ocean. I'll show you the next slide. This huge amount of warm water over here sitting above the cold water means you would have to dive deeper before you start to, if you had like a thermometer or something, before you would be able to start to measure any noticeable change in the, noticeable drop in the temperature. There's so much warm water that the thermocline is much deeper. Meanwhile, on the other side of the ocean, there's not so much warm water that the thermocline is much shallower, allowing for upwelling, something we talked about in the last lecture, to take place off the coast of Chile and Peru over here, which boosts the ecosystems and the fisheries on those coastal waters during a normal year. So there's high pressure in the Eastern Pacific, low pressure in the Western Pacific. And we talked about in the atmospheric section, everything goes from H to L, high to low, blow, blow, blow across the ocean. High pressure to low pressure, trade winds are going that way, the equatorial currents are going that way. Everything is going across the ocean on a normal year, forcing that pool of warm water to sit there on the Australian and the Philippine side of the Pacific Ocean, away from us. Now, during an El Nino year, that changes. That changes sometimes quite dramatically. That high pressure center in the Eastern Pacific, this H right here, that gets weaker. Sometimes this H and this L over here, they'll flip places entirely, okay? But nonetheless, it weakens. And so without a strong push from the high pressure in the east to the low pressure in the west, the trade winds aren't pushing as hard. And what allows, what happens here is that that pool of warm water actually starts to migrate over to the other side of the Pacific Ocean. If the high pressure and low pressure and the trade winds and the strong equatorial currents, everything was push, 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 push over here. During an El Nino year, the push to the west is much weaker. It's like push, 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 just stay over there. and that's not enough to hold the water in place. And so it will start to drift back to the eastern side of the Pacific Ocean. So what happens? That thermocline in the Eastern Pacific that used to be really shallow in a normal year becomes much deeper because that warm water shows up and it sits on top of the cooler coastal waters off the coast of Chile and Peru, displacing downward, pushing downward to that thermocline. You would have to dive deeper before you start to see your thermometer drop in temperature. Downwelling off the coast of Peru, the Peruvian fishermen and women are not happy during El Nino years because that downwelling takes the nutrients further from the surface. And when the nutrients aren't there, as we talked about in the last lecture, the whole rest of the ecosystem is just not going to be present in the numbers that fishing persons would want. This is kind of what it looks like. Here, we have completely swapped the high pressure and the low pressure. And so that warm pool, as you can see on the bottom diagram, it pools up on the other side of the ocean off the coast of the Americas, displacing downward, as we mentioned, the thermocline. And you'll see here with this big rain cloud above the low pressure area, as you would expect, something we've talked about before, low pressure is lifting, and lifting gives you the whole dance, which ends with rain. We get rainier seasons over here, specifically rainy winters during an El Nino year, because this low pressure is closer to our shores. In a normal year, like I just said, this is the pool of warm water will sit over there. And I think the next slide is going to be an animation that starts right away. So I'll move my cursor out of the way. But what I want you to look for when I click this next slide is the red and the white color indicating really warm water. It will start out over here closer to Australia. And then as the animation ticks through, you'll see that the time go by on the bottom. It's going to be months and months passing. During an El Nino year, you'll start to see that pool of warm water shift over to the other side of the Pacific Ocean. So I was right, it is an animation. Is it going to go? Is it animating? It's not. Now it is, there you go. So now we see that warm pool sitting over here off the coast of the Americas, and this purple and blue water off the coast of Australia and Indonesia and the Philippines and the surrounding area. That's the cooler water that during a normal year was held down much lower, but when the warm pool moves off the surface, the cooler water can come up and reach the surface. That's upwelling off the coast of Australia. So while there's downwelling off the coast of the Americas, and as I mentioned earlier, the folks who work in the fishing industry are not happy about that. The Australian fishermen and women, they're loving an El Nino year because that upwelling is nutrient rich and the fishing is just, it's bonkers. And then the third thing we have here is called a La Nina, a less famous part of this whole system. A La Nina is when essentially an El Nino will bounce back to normal, except when it bounces back so hard that sometimes it kind of overshoots the mark. So what happens during an El Nino? I'm gonna go back one slide to the animation to kind of illustrate a point about El Nino. Oops, there we go. So this pool of warm water, once I click it, it's gonna slide over here, and I want you to keep track of the time it takes. This is the 1998, 1999 El Nino. Oops. Let me get back. There we go. Oh, why is this not working? There we go. Now it's moving. So January, February, April, now it's on its way in late spring. And by July and August, you see the warm water pool up over there. The reason it takes so long, the reason this pool of warm water takes, somewhere between 6 to 12 months to find its way across the Pacific Ocean is something we mentioned before. To go against the flow of the equatorial currents, to go against the flow of the trade winds. It's not that the trade winds have changed their direction. They're still blowing. They're strong, consistent winds. They're just weaker. To go against the flow of the wind, to go against the flow of these currents, it's like, and some of you may have done this, for this pool of warm water to find its way to the other side of the Pacific Ocean, it's like trying to go up the down escalator. And if you're watching now and you've ever tried this, you're probably like, yeah, I remember trying to do that. It was probably for some of you, much harder than you realized. You got about halfway up and you're like, oh, I've made a huge mistake. But if you keep working, you can get there. You're just not going to go up the down escalator nearly as fast as you would go down the down escalator. When you're going against the flow, you can get there. It's just going to take a lot longer. And that's what an El Nino year is. This pool of warm water, it's going against the flow of the currents and against the flow of the wind, but it can find its way to the eastern part of the Pacific Ocean. It's just going to take roughly, as I said, 6 to 12, usually about 8 or 9 months to get there, which is great news for us, because the fact that it takes so long to get across the ocean, we over here off the west coast of the Americas, both in North America and South America, we can see that the El Nino winter is coming months before it actually gets here. So we can do some prep work. We can put some new tires on our car, expecting there's going to be a lot of rainy, slick roads out there. We can get ourselves a new umbrella if the old one we had was broken or whatever. We can just kind of plan for those El Nino conditions because it takes so long to happen. But now a La Nina is when we go back to normal. And now this is like running down the down escalator. You're going to go that much faster. Or it's like in an airport, those the flat escalators, the people movers. If you kind of walk along that, you have a very brisk kind of pace because it's like, and we're moving. You're going with the flow of the currents. You're going with the flow of the trade winds. And so that pool of warm water, when it returns back to its original position in the Western Pacific, it kind of flies over there. It goes there real quickly. And sometimes it will kind of overshoot its mark. It will go past its intended destination. And it will look something like this. This is the El Nino condition with the warm pool. Oops. Here, this is the warm pool over here in the Eastern Pacific Ocean. And then I'm just showing you, this is what it was in normal conditions, okay? Normal thermocline is right here. El Nino thermocline is down here. A normal thermocline is up here. And like I said, a La Nina, which can happen sometimes after an El Nino, it will look like this. You see how the thermocline is even shallower than it was normally off the Eastern Pacific? That's this kind of, not warp speed, but this faster speed of return. And you see that the pool of warm water is so aggressively splashed up against the western edge, western margin of the Pacific Ocean, that a lot of the warm water will actually peel its way northward through that Kuroshio current that we mentioned last time. And even some of the warm water, if you look down off the coast of Australia, it will actually wrap all the way around Australia. It really shoots past where it wanted to end up. And it just wanted to end up right here during a normal year. Okay, moving on. So the pattern of an El Nino, the full name is the El Nino Southern Oscillation. And those last two words always get left off, but they're telling you what's happening. There's something in the Southern Hemisphere, and the details of it we do not need to get into because it's really complicated, that flips back and forth. It oscillates. And when it oscillates, that high and low pressure system, they weaken and they sometimes change places. And so we can see that this oscillation takes place, giving us to some, in the past, some major El Nino events. But what we also notice looking at the pattern here, looking for a pattern here, is we don't see any pattern here other than the phases usually last for about a year to a year and a half, and that the pattern is highly irregular. Sometimes you can get one El Nino in a decade. Sometimes you can get three. You can have El Ninos, 2 years apart. You can have them 10 or 12 years apart. There's really no set, you can't like set your watch to it. There's no steady rhythm to it. But when they show up, as they did back here in 1983, I'll use my little laser pointer, that was a massive one. In the late 90s, 98, 99, that was a major El Nino. And I have some more modern data that I was able to pull here. We see another one here back in 2015, 2016. That's the more recent one that we had. That was the last time we had a really, really rainy winter. And it was those actually 2 consecutive rainy winters here in California, 2015, 2016, that ended the 5-year-long drought that we had been in, the really, really nasty drought where lakes were drying up and crops were withering and dying. That last El Nino we had was a massive one, and it was some much needed wet weather. But let's go back to this 1983 El Nino, and you can see what's happening. I put the temperatures here on your graph there in Celsius. So I'm going to move some stuff on my screen that you're not seeing, just so I can see what I'm talking about. We see here off the coast of, let's say, Orange County. It's in this kind of medium green, so about 13.5 degrees Celsius, which is 56.3 degrees Fahrenheit. The next winter, it went up to 59 degrees Fahrenheit, a temperature difference of 2.7 degrees. That's a noticeable temperature change. That's noticeable to you and I, somewhat, not that noticeable, but what's noticing that small temperature change very intensely are the smaller members, the microorganisms, the algae, the bacteria, even the small fish and the shrimp and the little microbes and things, the little tiny critters in the ocean. A 2 or 3 degree temperature change to them is very noticeable, potentially dangerous, potentially fatal, potentially catastrophic to those populations. And the other folks that notice that the temperature is warmer here are the warm water species, like warm water species of fish and eels and sharks, and those things, they start showing up off of our in our coastal regions, washing up onto our beaches and the like, because all they're trying to do, if you're, let's say, a tropical species of shark, is you're just trying to find your next meal, excuse me, and you're trying to find a mate when you're in the mood for that, and you're just trying to stay in water that you're comfortable with. That's it. The life of a shark, the life of a fish, the life of any marine organism is very simple: eat, reproduce, and stay healthy. And for them, staying healthy is staying in the temperature of water that's correct. So during an El Nino year, like we saw in 83 and 98, 99 and 2015 and 16, there were warm water species of sharks and warm water species of eels, and even there were like poisonous sea snakes washing up onto the beaches in Santa Barbara, LA, and San Diego counties. You can Google the news stories. It's kind of a wild time during an El Nino year, because we get visitors here along our coast that we just don't have any other time. And as I mentioned before, the winter season gets a lot wetter typically during an El Nino. Usually this wet weather moves northward through places like Portland and Seattle, places that are known for being kind of rainy and gloomy and foggy and overcast and higher precipitation. That wetness comes our way because the high pressure that's usually on our side of the ocean pushing that nasty weather further north or south, it's not there. So that nasty weather comes right onto our shores. Meanwhile, across the ocean, things really dry out in places like Australia and Indonesia and Southeast Asia, potentially leading to droughts, which we know here in California can then potentially lead to things like wildfires and the like. So I mentioned some of the animals showing up. There are high levels of coastal erosion because something you may recall from an earlier lecture, when there's warmer water, water expands when it's warmer. So sea level during El Nino winter, slightly, but somewhat is higher. It may be just like a quarter of an inch or half an inch, but just a little bit more water washing up onto our shores every time the waves crash. 10,000 waves hit the beaches roughly every day. That little bit of extra water gives those waves a little bit of extra oomph and power, and the erosive processes that can take place can lead to things like landslides, mudslides, cliff failures, and the like, which we're familiar with because we hear those stories during the really, really rainy winters. This is a comparison of the 1997 El Nino from satellite imagery and the 2015 El Nino. You'll notice one really big difference between the two is that in the Northern Hemisphere in 1997, which was a major El Nino, there wasn't as much warm water up off the coast of the United States and Mexico. But in 2015, we had a huge pool of warm water off the coast of the United States and Mexico. And there were as we know, warm surface ocean water is the fuel for hurricanes, and there were hurricanes showing up in this part of the ocean more regularly during the 2015, 2016 years than there had been in the years prior and since. Is this animated or no? I don't think it is. This looks like a temperature map. This looks like a temperature comparison between the 97 El Nino and the 2015 El Nino, but it's not temperature, it's height. This is what I was saying before, how when you have warm water, it actually expands, it actually expands due to the extra heat, and sea level is actually slightly higher, 200 millimeters higher, which is 20 centimeters, which is about 8 inches. 8 inches of extra water out here in the ocean, and about 8 inches lower ocean waters on the other side of the Pacific, where it was cooler and thermal contraction takes place. Okay, that's it for El Nino. The last, the third of the 3 topics that we're going to talk about is the thing I mentioned at the very beginning of the previous lecture. I said 90% of the ocean water undergoes thermohaline circulation. And I said in the last video, if you watched the last video, hopefully you did, that we only needed to spend maybe 5 or 10 minutes talking about it. And this is that 5 or 10 minutes because it's very straightforward. If water is denser, it will sink. If other water is less dense, it will float. That's it. We know this. And we also know how you can make water denser. You can either make it, let me turn this off. You can either make the water colder, and that will make it denser, or you can make it higher salinity, and that will make it denser. Or if you make it cold and salty, you made it really dense. So that's what we're looking at here. It's that simple. Warm water floats, fresh water floats, cold water sinks, salty water sinks. And this is thermohaline circulation. The waters in the deep ocean, everything below the surface waters, below the pycnocline, will flow according to these density properties. But what we can do is we can actually separate those deep waters into individual water masses according to this thing called a TS diagram, which stands cleverly for temperature and salinity. We're going to plot the temperature range and the salinity range of these deep ocean water masses, and we can compare them to one another. The reason we can do this is because the water is very slow to change its character, change its identity. It's like your parents sometimes, or your uncle who are just set in their ways. You know they're wrong, but they're never going to change. They're just going to be who they are. These water masses, when we set the temperature and we set the salinity to be in a certain range, they'll stay that way for a long, long time. So we can plot these on this TS diagram. It's showing you, there we go. Temperature plotted here on the y-axis, salinity plotted here on the x-axis. As you go left to right, salinity is increasing. If you look at those numbers, as you go bottom to top, temperature is increasing. If you look at those numbers. And then the third thing we see on this diagram are these blue lines. These numbers here are your densities. The densities given a certain temperature and a certain salinity, you will get a certain density. And down here in the bottom right corner, you'll see that the density number 1.0290 is the highest density number because that is the saltiest water according to the salinity, and it's also the coldest water. Repeating what I literally just told you, really cold and really salty water should be really dense water. The opposite top left corner of this diagram, we see it's the warmest water, which should make it less dense, and it's the least salty water, which also makes it less dense. And so, no surprise, that's where the lowest density numbers are. This orange, what shape is that? A parallelogram? Yeah, parallelogram. NACSW, North Atlantic Central Surface Water, is literally what we talked about the entire last lecture. It's the big whiteboard that I had off to my side that I was drawing on. That is the North Atlantic Central Surface Water. A range of salinities, a range of temperatures. We already talked about it. I'm over it. We're not talking about that water anymore. That little green parallelogram, we'll get to that later. That's the Mediterranean. What I want to focus on are these relatively, and they're more squarish shapes. The AAIW stands for Antarctic Intermediate Water. The AABW stands for Antarctic Bottom Water. And the NADW is the North Atlantic Deep Water. These are three different masses of water or layers of deep water in the ocean. And if you look really closely, I want to point out to you right here that the pink square, the AABW, the Antarctic Bottom Water, it's actually crossing this 1.0280 density line. So of those three squares, roughly, it's the densest one. And if you're the densest layer of water, where are you supposed to be? On the bottom. What's this water called? The Antarctic Bottom Water. It tells you where it is. And now we know why it's down there. It's on the bottom because according to this diagram, it's the densest one. Why is it the densest one? Is it the saltiest of these three? No, it's not. You can see the North Atlantic deep water has a salinity closer to 35 parts per thousand. Antarctic bottom water is a little bit less salty than that. But what it does have, the advantage it does have over the other two masses, is it's colder. It's actually at zero, if not slightly below zero temperature. The reason salt water, as we mentioned before, the reason salt water can actually drop below freezing is because the salinity in it will change the freezing point. Fresh water would have frozen at zero. Salt water freezes at a different temperature than that. The other thing that's going on here is because we're on the bottom of the ocean, the pressure is extraordinarily high. And as we know, for water to freeze, it has to overcome that salinity, which isn't easy, and it has to expand. Water expands when it freezes. Remember how crazy ice cubes are? It can't expand when the pressure at the bottom of the ocean is so incredibly great. So it stays liquid even though it's below its freezing point because the pressure is so great. So we call it now, the other part of the name is the Antarctic bottom water. It's because it forms off the coast of Antarctica. Here, I'm going to skip ahead a slide. If you recall from the previous set of video lectures, I mentioned those things called the subpolar gyres. There were these little two spots right here off the coast of Antarctica where that surface water will just circulate and spin around, getting colder and colder and colder and colder. And once it gets cold enough, it will be dense enough and it will sink, it will drop. And that's what we see here. It's like a vertical, it's just an elevator shaft. It just drops all the way to the bottom. And once it gets there, it has nowhere to go. And so it starts to flow away from Antarctica. In this case, obviously northward, because everywhere is north from Antarctica. And it moves northward along the bottom of the Atlantic Ocean underneath all of the other layers of water. The North Atlantic deep water, that's forming from these other subpolar gyres up here off the coast of Greenland and north of Iceland there in the Arctic Ocean. Again, the water's swirling and spinning on the surface, getting colder and colder and colder, and then it drops down. And it drops down towards the bottom of the Atlantic Ocean, but not all the way there, because what's lying on the bottom of the ocean? The Antarctic bottom water with a higher density than the North Atlantic deep water. So the North Atlantic deep water will take this second deepest spot in the ocean. And like the Antarctic, it has to flow away from there. In this case, it starts in the north, and so it will flow to the south. And then the third body of water that we see here, the AAIW, the Antarctic Intermediate Water, it's also forming and sinking off the coast of Antarctica. But as you see here, because the temperature isn't as cold and the salinity isn't as high, it doesn't sink as far. It takes this intermediate, kind of this middle layer in the ocean, and it will float down. Sorry, it will sink down underneath the surface water, but it will float on top of the North Atlantic deep water. So you can see these three water masses. Antarctic intermediate water is, of the three, the least dense. North Atlantic deep water is slightly denser, and the Antarctic bottom water is the densest. And they will make layers bottom all the way up towards the surface according to those different densities. The pink layers that you can see here up at the surface, that's what we were talking about in the last lecture. We don't need to talk about it anymore. We've already covered it. It's the orange section on this TS diagram. Skip. Okay. I mentioned the Mediterranean. We'll just skip it for now because we're not going to see that on an exam or anything. Okay, so as I mentioned, the water masses, when they get really cold or they get really salty or they get really warm or they lose their salinity, they tend to stay that way for a very, very long time. Like I said, once they are who they are, they're going to stay that way. And so when this deep water sinks towards the bottom of the ocean, that Antarctic bottom water, it will stay down there for 1,600 years. There is water in the Antarctic bottom water current that just now is coming back up to the surface, and it's been down there since the year 400. I don't study history very much. I don't even know what was going on in the year 400. I don't know, ancient Greece, maybe, stuff like that. That water has been down there since then. And it's just now popping its way up to the surface as new water is sinking and displacing it. It's finding its way up to the surface, looking around me. I'm like, holy crap, this place is way different than it was 1,600 years ago. The other deep waters, the North Atlantic deep water and the Antarctic intermediate water, they're down there for 2 or 3 centuries. They're only moving 1 or 2 meters per day. Compare this rate of movement to what we were talking about in the last lecture, how the North Atlantic subtropical gyre, I said that those currents are moving either slower than, faster than, or about the same speed that you can swim. I'm guessing every one of you, even not the strongest swimmers amongst you, can swim more than 1 to 2 meters in 24 hours. 1 to 2 meters. I mean, that's 3 to 6 feet, and it takes 24 hours. It's a real slow, almost imperceptibly slow movement. And that's not even the bottom water. The bottom water is, what is that, 8 times? Yeah, I'm trying to do the math in my head, 6 to 8 times slower than that. Again, it's almost imperceptibly slow that the water's moving down there. So we can kind of essentially think it's standing perfectly still, even though there is some deep ocean currents. These are called, again, thermohaline circulation currents. So thermohaline circulation moves very slowly, but also very predictably. If you can find the denser water, you can find the colder water and the saltier water, thus the denser water, you know where it's going to go and you know where it's going to move. And the only thing that's going to move it along the seafloor is new, colder, saltier, denser water sinking down to displace it. So once you find your way to the bottom, new stuff finding its way down there, that's what kind of keep this train going, this current moving along the deep ocean. And so what we get, I'll go back real quick to a previous slide, is we get this thing called, it's called a conveyor belt, essentially, this conveyor belt circulation. We have these surface waters tracking these, the surfaces, and then these subpolar gyres, this is where they will sink and leave the surface, head to the bottom of the ocean. As we just saw, they'll stay there for centuries, sometimes more than 1,000 years before they actually ever come back up to the surface. So circulation is really slow, if you haven't picked up on that by now. And that's it. We talked about, so to review, we talked about the monsoons, specifically in the Indian Ocean and the surrounding regions of the Indian Ocean, and how that changes with when the ITCZ changes its position from the north to the south and back and forth every year. And then we moved over to the Pacific, and we talked about how the El Nino works and why that happens and how that happens and the effects of that happening. And then as we just finished talking about thermohaline circulation, salinity, temperature, and density differences in the water masses lead to those water masses sinking and flowing in the deep ocean according to those density contrasts. That's it for chapter 7. So I'll leave this video here, and we will pick up chapter 8 material, which is waves, in the next lecture. See ya.